Hello everyone. Welcome to Power Systems Analysis Lectures. I'm Sonal Fernando and I'm an electrical and controls engineer based in the UK with a background in power systems and control. In this lecture series, I'll walk you through the fundamentals of power systems analysis, starting off with the per unit system applied for single phase systems. In this lecture series, we will cover what is the per unit system and why do we use it. We'll look at the principles that need to be applied when we utilize the per unit system for power systems analysis, particularly with the selection of what we call as these base values. To top it off, we'll do an example of the per unit system applied for a single phase system analysis. This will give you a good fundamental understanding of how we can actually apply the per unit system for power systems. Let's have a brief look at of what an actual power system consists of. You might already know that electrical energy is generated at a power station, and this generated electrical energy is stepped up to high voltages via a step up transformer and transmitted via transmission lines to distribution substations. At the distribution substation, the voltage is stepped down again to usable values and then distributed to various loads like housing and general industrial and commercial loads. To get a better understanding, let's dive a bit deeper into this power system. Typical power systems, as the one shown in this figure, are three-phase systems. To get a more simplified representation of such a system, we can draw the single line diagram for this system. First, we have the power generator, which is typically represented by an AC voltage source in the single line diagram. Next up, we have the step-up transformer. Let's label it as T1. This transformer is then connected to a transmission line as shown here. Followed by the transmission line TL, there is the step-down transformer. Let's label it as T2 for ease. Finally, we can represent the electrical loads in the single line diagrams. Electrical loads can be represented as impedances and are simply combinations of resistances and reactances. Therefore, let's represent these loads as impedances. Typically, the letter Z is used to denote the impedance. Hence, these loads can be labeled as ZL1, ZL2, ZL3, etc. Depending on the number of loads present, you can keep adding them into the single line diagram. This section here is the load bus bar, where the voltage is distributed between the loads. As power systems engineers, the voltage at the bus bar and the current coming into the bus bar is of great interest to us. Therefore, we need to work out, starting from the generation point, how much voltage is received at the bus bar. In order to do this, it is necessary to draw the equivalent circuit diagram from the single line diagram. The equivalent circuit diagram models components such as generators, transformers, loads using accurate electrical parameters like resistances and reactances for more detailed analysis. Let's start with the generator. A generator is represented with a voltage source, let's say Vs for example. The generator has coil windings, which we can represent with their constituent resistance and reactance as shown. Next up, we have the transformer. Before proceeding any further, let's take a quick look at the transformer equivalent circuit. A transformer has a primary side coil, a secondary side coil, and a transformer core. If we want to draw the equivalent circuit of the transformer, we need to first represent the primary side coil winding with its constituent resistance and reactance. Let's say R1 and X1. The transformer has a metallic core. We can represent the core as a shunt resistance and reactance like this. Let's denote the voltage on the primary side as V1 and the current on the primary coil as I1. There is some leakage current in the transformer core, however, we can typically neglect this current. Let's say, for example, the primary side has N1 turns. Similarly, we can represent the secondary side coil winding using its constituent resistance and reactance as shown. Let's represent the voltage and current on the secondary side as V2 and I2 respectively. The number of turns on the secondary side coil will be N2. So this right here is the transform equivalent circuit. Maybe you can see that drawing this equivalent circuit all the time for analysis can be quite time consuming. What if we can somehow bring the secondary side resistance and reactance to the primary side? Maybe let's say as R2 dash and X2 dash. In order to do this, we assume that there are no power losses in the transformer. So if that is the case, then the power dissipated by R2 dash would be I1 squared R2 dash. And since this is a lossless transformer, this should be equal to I2 squared R2. So if we look at this carefully, we have now found an equivalent resistance R2 dash on the primary side that would dissipate the same power as R2 would on the secondary side. Hence, we can now find the resistance R2 dash in terms of secondary side resistance R2 as shown. This term here is the transformer ratio, which can be expressed in terms of the number of turns on the primary side and the secondary side, as well as the currents. We can do the same derivation for the secondary side reactance as well. Let's quickly represent that here. For ease, let's represent the transformer ratio as K. Through this exercise, we have found an equivalent resistance and reactance of the secondary coil winding that can be reflected on the primary side. Using these new terms, we can draw a simplified equivalent circuit for the transformer model. First, we have the primary side resistance and reactance, followed by the transformer core. And now you have the secondary side resistance and reactance reflected onto the primary side. The primary side voltage is V1 and secondary side voltage is reflected to the primary side as V2 times K. As you can see from this figure, this is much more simplified compared to drawing two separate coil windings all the time for a transformer. Now that we know what a simplified transformer circuit looks like, let's get back to drawing the equivalent circuit. We have the primary side coil winding, resistance and reactance. Let's denote them as RT1 and XT1. The transformer core can be represented using the equivalent shunt resistance and reactance. And similarly, let's denote the secondary side winding resistance and reactance referred to the primary side like this. Let's quickly section these out for more clarity. Next is the transmission line. A transmission line can be modeled as a combination of resistors, capacitors, and inductors, depending on the length of the line. We will look at transmission line modeling in a future lecture. For now, let's model the transmission line as simply a resistance and a reactance. Then we have the step-down transformer T2. The equivalent circuit model is the same as the step-up transformer T1, only the values of the resistances and reactances change here. Finally, we have the loads. As I mentioned before, let's represent these loads as impedances, which is once again a combination of resistances and reactances. Let's also label the voltage and current of the load bus bar. So if we are to find out these values, we have to start from the generated voltage from the generator, work your way through all these circuit elements, and then find out the load bus bar voltage and current. I think you can already see this is not a straightforward task and can take some effort to do this. And not only that, remember we only drew the equivalent circuit in single phase. In actual world problems, we typically deal with three-phase systems. Unless the three-phase system is perfectly balanced, you will have to draw three of these circuits. This can be a cumbersome exercise. Also remember that the power system we are analyzing here is a very simple one, with only one generator, a couple of transformers, a transmission line, and some loads. In real life, these are not as simple as in this figure. In fact, if we look at a system that closely relates to a real-world power system, this figure gives a better picture. Notice how many generators, transformers, bus bars, and transmission lines are present here. Imagine obtaining equivalent circuits and solving them for such a system. Even with the computational power we have nowadays, this can be a daunting and sophisticated task. Hence, we need to come up with a better and more efficient way of doing this. Enter the per unit system. The per unit system is simply a way of normalizing power system quantities to a given base value, which can greatly simplify numerical calculations. Let's take a voltage source like a generator like this for example. It is rated at 20 kilovolts but operating at 18 kilovolts. Hence, we can simply get the normalized value of the operating voltage by dividing it by the rated voltage. Simply put, this is the per unit value of the operating voltage. As you can see, per unit value is dimensionless. If you prefer, you can write PU just to denote that this is a per unit quantity. We can also represent it as a percentage. So, from this, you can see that the definition of the per unit system is the actual value divided by the base value. An important thing to note here is that since we are dealing with AC quantities in power systems, the actual values can be complex numbers. However, remember that for the definition of a per unit value, the base value has to be a real value. Now that we know what a per unit value is, we can start applying them to analyze power systems. To apply them for power systems analysis, there are a few simple rules to follow. On the previous slide, we saw that we can select a base voltage to obtain the per unit value of a voltage. Similarly, we can select base values for other power systems quantities as well, like power, current, impedance, etc. For the analysis of a power system, we need to select two independent base quantities. Typically, we select the apparent power base and the voltage base for this purpose. The other base values can be obtained using these two bases by the application of fundamental circuit laws as shown. The active, reactive, and apparent power bases are identical. The current base and the impedance bases can be calculated as shown. The important thing to note here is that all these quantities are per phase quantities, not three-phase values. Let's quickly revisit the basic power system we were looking at before. If we are going to apply the per unit analysis to this system, first we must select a base value for the apparent power. Let's say S base. For per unit analysis, the S base remains the same throughout the power system. On the other hand, when selecting a V base for the voltage base is taken for each side of a transformer. So if the base voltage on the primary side is this, then we can use the transformer ratio to calculate the secondary side base voltage in this manner. Let's apply what we have learned so far to the single phase network shown below. This network contains two transformers T1 and T2. Given the presence of these transformers, we can divide this network into zones, since we know we can find the voltage bases on either side of each transformer. In fact, this network is often referred to as a three-zone network. As the question says, we have to draw the per unit circuit and determine the per unit impedances and the per unit source voltage. Then we can calculate the load current in per unit form and in amperes. For ease, as stated, we can neglect the transformer winding resistances and shunt admittances. So, for a per unit analysis, based on what we discussed, you know that we have to select two independent base values. Typically, we can select an apparent power base which remains the same throughout the power system. In the question, they have asked us to select the apparent power base as 30 kilovolt amperes. Next, we can take the second independent base as a voltage base. We can find the voltage base for each zone. For example, let's say the voltage base of zone 1 is VZ1 base. The question states that the voltage base of zone 1 can be taken as 240 volts. For ease, we can write the zones separately in this manner and formulate each section. First, we can start with the voltage bases. As the voltage base of zone 1 is already given, we can find the voltage base of zone 2 next. Let's denote this as VZ2 base. To find the VZ2 base, we can use the transformer T1's turns ratio. The transformer ratio of T1 is already given to us in the figure above. Then we can find VZ2 base as follows. Similarly, we can also find the base voltage of zone 3. Let's represent it as VZ3 base. Similar to the previous scenario, we can use the transformer ratio of T2 now to find VZ3 base. Let's quickly work it out here and obtain the VZ3 base. So through this exercise, we have found the voltage bases of zone 1, zone 2 and zone 3. As one of the objectives is to draw the per unit impedance circuit, we can find the impedance bases of each zone. Let's call these the Z bases. One thing to note here is that in the generator in this power system, there is the generator winding resistance and reactance. However, for this question, they have not given the per unit winding resistance and reactance values, and therefore you can neglect them for now. Since these are not required, you actually do not need to find any base values for zone 1. We only need to find the impedance bases of zones 2 and 3. Let's denote the zone 2 base impedance as Z2 base. We can find Z2 base using the base voltage of zone 2 and S base as follows. From this, we get the following Z2 base, and remember that a base value always has to be a real number. Similarly, we can also find the zone 3 base impedance Z3 base using zone 3's base voltage and S base as follows. Now as you can see, we have found the base impedances of zones 2 and 3. Using these values, we can work out the per unit impedances. First, of course, we have the voltage source, but as mentioned before, we can neglect this. Second, we have the transformer T1. In the figure, they have already given the per unit impedance of the transformer T1 as 0.1 per unit. Typically, the transformer's per unit impedance is given on its nameplate. And this per unit impedance is given with respect to its rated values. So for this transformer alone, the rated values can be taken as its base values. You already know that in this question, S base is to be taken as 30 kilovolt amperes, and since the transformer T1 is in zone 1, VZ1 base is 240 volts. So you can see that the base values that we have obtained and the transformer ratings are identical. In that case, we can use the per unit impedance already given for transformer T1 on its nameplate. Just to be more specific, let's denote the impedance of transformer T1 like this. A quick side note, you can see in this question that they have given a per unit equivalent impedance. But by now we know that the transformer has a primary and secondary side impedance along with the shunt components. In most transform equivalent circuit questions, the shunt resistance and reactance can be ignored because the leakage currents are almost negligible. Hence, we are left with a further simplified version like this. From this circuit, you can see that it is possible to take an equivalent resistance and reactance based on the values in this manner. Of course, from this the equivalent impedance can be calculated as follows. As this is the actual transform equivalent impedance, we can use the corresponding base impedance to calculate the per unit value as shown. This is what they have given in this question as a per unit equivalent impedance for us to utilize. Now let's look at transformer T2, which is a different scenario compared to T1. T2's ratings and the per unit impedance are given here. Like T1, T2's per unit impedance is given with respect to its own ratings. The transformer T2 is in zone 2 and we have found some new base values for zone 2. Now if you compare the ratings of T2 with the base value of zone 2, you can see that they are not the same. Therefore, we have come to a point where we should convert this existing per unit value to a new value with respect to the new bases that we have found for zone 2. To convert the so-called old per unit impedance to a new per unit impedance, we need to obtain the corresponding old base impedance. You already know that from the definition of per unit, we can get the actual value of an impedance in this manner. Let's write two columns, one representing the old bases and per unit values, while the other represents the new bases and per unit values. In either case, the actual impedance of the transformer does not change, since of course the transformer remains the same. So for the old side, you can write the actual impedance as follows. Similarly, on the new values side, you can once again denote the actual impedance Z actual now using the new values. In both cases, the actual impedance remains the same. So we can equate these two equations and we get the following. So we can find the new per unit value after some manipulations like this. Z old base can simply be obtained using V old base and S old base, and similarly Z new base can be obtained using the V new base and S new base. There we can work out the new per unit impedance value in this manner. This is a common equation that is used in per unit analysis to find new per unit impedances from the old values. To be more specific to transformer T2, let's call its new per unit impedance ZT2 per unit. For this transformer, the old per unit impedance is the one they have already given in the question here. Similarly, the V old base and S old base are the nameplate ratings. We can take the primary side coil voltage of T2 since the transformer is in zone 2, and the V new base is now the base voltage of zone 2 that we have found before. S new base is 30 kilovolt amperes, which was already given to us in the question, and S old base is the base power rating of the transformer. By working this out, we get the new per unit impedance of transformer T2. Next up, we have the transmission line TL, which is in zone 2. Therefore, to obtain the per unit reactance, we can simply take the actual value and divide it by the base value. We already found the base impedance of zone 2, which we can use here. Hence, we can calculate the per unit reactance of the transmission line. The impedance of the transmission line is simply the reactance with the complex operator J. Finally, we have the load which is present in zone 3. Just like we did with the transmission line, we can use in this case zone 3's base impedance to find the per unit impedance of the load like this. Now, using the calculations we did thus far, we can draw the per unit circuit. First, we have the generator. We can find the per unit voltage of the generator using the base voltage of zone 1. Let's draw the per unit equivalent circuit now. First, start with the generator and denote its per unit voltage. This is followed by the transformer T1 and its corresponding per unit impedance. Next, we have the transmission line TL, which is followed by the transformer T2. Finally, we have the load in the system. This here is the per unit equivalent circuit of the power system. As you can see, all quantities in this circuit are in per unit form. We can also represent the current supplied by the generator as IS per unit and the load current as I load per unit. Of course, as this per unit circuit is in series, the supply current and the load current are equal. So if we want to find the load current, we can apply Ohm's law to this circuit, where the current is equal to the supply voltage divided by the total per unit impedance, which in this case is basically the sum of all the per unit impedances in the circuit. From this, we can work out the load current per unit value as shown here. From this per unit value, if you want to find the actual value of the load current, that is the current in amperes, we can once again use the definition of a per unit value here. To find the actual value of the load current, we need to know the corresponding base value of the load current. The load current is in zone 3, hence we can find the base load current using S base and the zone 3 base voltage. By working this out, we can get the load current base value as shown here. From this, we can find the actual load current by substituting the base load current in this manner. In this lecture, we introduced the fundamentals of the per unit system and applied them to analyze a single phase network. By converting the network to its per unit equivalent circuit, we were able to simplify the calculations and determine important quantities such as the load current with relative ease. While our example focused on a simple single phase network, the real strength of the per unit system becomes apparent when analyzing larger and more complex power systems. Per unit quantities are widely used in power system studies, including load flow analysis, fault analysis, and the modeling of interconnected networks containing generators, transformers, transmission lines, and loads. In the next lecture, we will extend these same principles to the three phase power systems. You will see how the per unit system provides a consistent framework for analyzing three phase networks and how it significantly simplifies calculations that would otherwise be much more involved. Thank you for watching, and I look forward to seeing you in the next lecture.